Something's not right about 3I to Atlas. In late July, flagship space telescopes like Hubble and JWST captured extraordinary data on this rare interstellar comet. Just as its coma ballooned past 300,000 kilometers, with reports of a greenish glow and strange bursts of brightness, the stream of official updates suddenly stopped. NASA explained it as a matter of solar geometry and safety rules, but the silence still feels unusual. The contrast is striking. When Oumuamua appeared, and later Borisov, the world was fed a steady stream of rapid updates and dramatic images. This time, the information vacuum is noticeable, and it fuels speculation. Without timely answers, public trust in how discoveries are revealed begins to erode. What exactly is behind this blackout? And what are we not being told about 3I Atlas? On July 21, 2025, the Hubble Space Telescope locked onto this interstellar visitor, capturing its sharpest images yet. Less than 3 weeks later, on August 7th, those images were released, showing a nucleus no larger than 5.6 kilometers across, surrounded by a sprawling dust plume stretching toward the sun. Soon after, JWST pointed its NR-spec instrument at the comet, gathering spectra. But for the public, only dry technical notes and brief comments were shared. No headline images, only hints that deeper analysis was underway. Even Gemini South joined the effort on August 27th, delivering images that confirmed the comet's activity and shifting tail. Those were placed in public archives by early September, sparking excitement online. And then, just as the world was watching closely, the cadence changed. By late September, there were no new flagship releases, no fresh data, only silence stretching wider with each day. This is where the mystery deepens, not just in the comet itself, but in the growing silence surrounding it. I'm Mike, and this is Lumora. The first round of data painted a picture both familiar and strange. Hubble's images from July revealed a nucleus no larger than 5.6 kilometers across, tiny in cosmic terms, yet surrounded by a coma so immense it stretched more than 300,000 kilometers, far larger than most comets at that distance. That single observation set astronomers buzzing. A dust plume arced sunward, shimmering against the black sky, and hinted at powerful outgassing shaping the comet's early behavior. Then came Webb. On August 6th, the James Webb Space Telescope gathered spectra with its NIR-spec instrument, promising a closer look at the comet's chemistry. But what reached the public was thin. A few technical notes, vague mentions of ongoing analysis, no dramatic images. The silence stood in contrast to the excitement that usually follows Webb's breathtaking views. Even with just scraps of information, whispers began. Some scientists hinted at an unusually strong carbon dioxide signal, far different from the water-dominated comas typical of local comets at similar distances. If confirmed, it would be a major chemical clue, one that might reshape how we think about icy bodies entering the solar system for the first time. Meanwhile, ground-based observations filled some of the gaps. On August 27th, Gemini South caught the comet in action, confirming its evolving tail. Those images entered public archives by September 4th, and for a moment, they reignited interest. The sprawling coma, the shifting dust features, the hint of green tint, all of it fueled online discussion. But after September 22nd, the flow began to fade. Hubble and Webb went dark, not because they wanted to, but because of geometry. The comet had crossed too close to the sun's line of sight. At first, the public didn't notice. But for those following closely, the absence was glaring. The cadence of discovery slowed, and what began as steady, thrilling releases slipped into silence. Observing a comet like 3I Atlas with Hubble or JWST isn't as simple as pointing a telescope and clicking a shutter. Both orbiting observatories are bound by strict solar avoidance rules, hard physical limits designed to protect their sensitive optics from the lethal glare of the sun. For Hubble, the boundary is clear. No observations within 50 degrees of solar elongation. Webb's constraints are even tighter. With its massive sunshield and delicate infrared sensors, JWST cannot observe targets within 85 degrees of the sun. These numbers aren't negotiable. They're built into mission planning software and enforced by automatic lockouts. If a target drifts too close to the danger zone, the system simply refuses to schedule the observation. Any attempt to override the rules would trigger safing protocols, shutting down science operations until a full review could be carried out. The risk isn't hypothetical. A misstep could permanently damage the detectors, or in the worst case, end the mission altogether. By late August, 3I/Atlas had slipped beyond Hubble's 50-degree margin, and not long after Webb's August 6th run, the comet crossed the 85-degree threshold for JWST. From that point forward, both flagship telescopes were locked out. There was no decision to withhold data, no conspiracy, just geometry and physics. The only solution is to wait for the comet to move far enough from the sun's position in the sky to reopen the viewing window, a realignment that calculations show will not arrive until early December. This enforced blackout explains much of the silence. Yet for the community watching closely, the gap still feels unsettling. Each day without new images feeds speculation. When the instruments go quiet, the void is quickly filled by theories, doubts, and rumors. What is out there, unseen in the weeks that follow, and will the December window reveal something profoundly new or simply confirm what little we already know? Even before the blackout began, the first fragments of data hinted at something unusual. Hubble's July images didn't just reveal a dust tail, but a sprawling coma stretching nearly 348,000 kilometers across, more than a quarter the diameter of the Sun. For a comet still far from perihelion, that size was extraordinary, a signal of intense activity for such a small nucleus. The earliest whispers from spectroscopic analysis suggested another surprise, a possible dominance of carbon dioxide. While no peer-reviewed results had been published by late September, multiple observers noted that the teams hadn't denied the hints. If true, this would set 3I/Atlas apart from most local comets, which tend to be water-dominated at this range. It could mark the first strong chemical clue to an interstellar comet's true nature, preserved from a distant system and never before exposed to the sun's heat. Meanwhile, amateur astronomers tracked the comet from Earth with smaller telescopes. Many reported a distinct greenish tint in the coma, a classic hallmark of molecules like diatomic carbon or cyanogen. But the color was brighter, more persistent than usual, sparking debates. Was it just a trick of viewing geometry, or evidence of chemistry unlike anything we've cataloged? The sunward plume added another layer of intrigue. First caught by Hubble and then Gemini, its shifting shape and brightness seemed to change night by night. Some argued it was driven by surface outbursts, jets blasting fresh material into space. Others pointed to changing angles between the comet, Earth, and the sun. Even the brightness curve, or photometry, defied easy answers. Amateur and professional measurements often disagreed by more than a full magnitude. Some of that scatter came down to equipment and calibration, but part of it may have been real. Rapid fluctuations in the coma, or sudden bursts from the nucleus itself. With the flagship sidelined, these oddities became the only clues we had. A vast coma, possible CO2 richness, persistent green color, and a shifting plume, all pieces of a puzzle that refused to settle, each one fueling speculation about what exactly 3I/Atlas might be. By late September, the silence around 3I/Atlas was no longer just a technical matter. It had become deeply personal for the global community of skywatchers. Social media feeds, astronomy forums, and late-night live streams filled with frustration and speculation. One amateur astronomer confessed, "It's like chasing a ghost. Every night we're guessing what's actually happening out there." Another simply asked, "Why can't we just see the raw data? What are they waiting for?" The truth is that every observation from Hubble or Webb enters a long, intricate pipeline before anyone outside the instrument teams can see it. Once downlinked, the data undergo calibration, removal of cosmic rays, correction for detector quirks, and background subtraction. For Webb, this process is even more demanding, with multiple stages of software analysis and artifact checks. A single missed step could mean announcing a chemical signature that isn't real. Policy adds another layer. Both Hubble and JWST operate under proprietary periods, 6 months for most Hubble programs, up to a year for Webb. This gives the principal investigators who designed and won the observing proposals the first chance to analyze the data. Some teams release information quickly, but many hold back until they are confident. For a target as high-profile as 3I/Atlas, caution becomes almost a duty. One Webb co-investigator summed it up. "It's better to be right late than wrong fast. With interstellar targets, there's no second chance." But from the outside, this careful pace feels like a wall. The longer the silence stretched, the more routine caution looked like secrecy. Conspiracy theories blossomed. Maybe classified satellites had captured images too sensitive to release. Maybe agencies were withholding data to prevent panic. Maybe the truth was simply too strange to share. In reality, the machine was grinding forward step by step. Yet in the absence of updates, the perception of a void grew stronger. The blackout wasn't just a gap in data, it was an open canvas for imagination, suspicion, and unease. Behind the curtain of silence lies a process that is anything but simple. Every observation from Hubble or JWST begins its life as raw spacecraft telemetry, files crowded with cosmic ray strikes, detector noise, and background distortions. The first step is calibration, scrubbing cosmic ray hits, correcting for sensor quirks, and subtracting the glow of the scale. For Webb's NIRSpec, there are at least 3 major stages, from detector-level corrections to advanced artifact rejection. Each checkpoint requires teams of scientists and engineers to verify the results, sometimes rerunning the pipeline when something looks off. Only when the data reach a science-ready state do the principal investigators even get to review them. And here another bottleneck appears, the proprietary period. Hubble programs generally allow 6 months of exclusive access, while Webb can grant teams up to a year. This is not bureaucracy for its own sake. It's a reward for years of planning, proposal writing, and competition, but it means the public often waits, sometimes far longer than expected. After the investigators and their teams are satisfied, the files move into yet another stage, agency review. NASA, ESA, and sometimes CSA must all sign off on headline releases. They check for contractual obligations, coordinate timing, and weigh the risks of releasing ambiguous findings. Even non-controversial data can sit for weeks in this loop. When results hint at something surprising, as some suspect with 3i Atlas, the review slows even more. The contrast with earlier interstellar visitors is sharp. When Oumuamua appeared in 2017, raw data and preprints spilled into the public within days, sparking open debate and wild speculation. Borisov, discovered 2 years later, followed a steady cadence with regular images and spectra. But with 3i Atlas, the combination of proprietary locks, painstaking review, and multi-agency coordination has produced a fragmented stream. From the outside, this rhythm feels like a vacuum. From the inside, it is a cautious march to prevent mistakes. Every stage is built not to hide the truth but to protect the integrity of science. Still, for those watching, the delays turn into fuel for suspicion, and each pause in the timeline deepens the sense of mystery. Amid the silence from Hubble and Webb, the next big opportunity arrives not from Earth, but from Mars. On October 3rd, 3i Atlas will pass just 0.19 astronomical units from the red planet, about 28 million kilometers. That's close in cosmic terms, but still far beyond the range where cameras can resolve detail. The Trace Gas Orbiter, famed for its sharp 5-meter-per-pixel views of the Martian surface, will see the comet as nothing more than a faint point. Even HiRISE on the Mars Reconnaissance Orbiter, with its larger aperture, can only sharpen resolution to about 34 kilometers per pixel, still far too coarse to pick out the nucleus or the structure of the coma. The value of this flyby lies not in dramatic close-ups, but in coverage. From Mars orbit, these spacecraft can take brightness measurements at a time when Earth-based observatories and the flagships are locked out by solar geometry. A sudden jump in brightness could signal fragmentation, an outburst, or volatile release, clues impossible to ignore. And unlike the slow release pipelines on Earth, data from Mars orbiters can be downlinked and processed in a day or two, offering near real-time glimpses into the comet's behavior. Then comes the bigger test, perihelion. On October 29th or 30th, 3i Atlas will pass about 1.36 astronomical units from the Sun. It won't be a classic sungrazer, but the heat and speed will place immense stress on the nucleus. If the comet survives intact, we may see its coma brighten, its tail shift dramatically, or its color profile change as surface ices vaporize. Observers will be watching for 3 key signs: spikes in the light curve that could mark fragmentation, changes in the anti-tail orientation as geometry shifts, and any alteration in the comet's greenish hue. Each would tell a story of chemistry, dust dynamics, and survival under solar fire. And in December, when the comet drifts far enough from the Sun to re-enter Hubble and Webb safe zones, the world will finally get fresh flagship images. Until then, the Mars flyby and perihelion are the chapters that must carry the narrative forward. For now, the mystery of 3I Atlas sits in a strange limbo, shaped by technical constraints, data pipelines, and institutional caution as much as by the comet itself. Hubble's 50-degree and Webb's 85-degree solar avoidance rules are non-negotiable, hardwired to protect the instruments. The multi-week calibration process and long proprietary periods keep data in the hands of investigators before the public can see them. Each press release must clear layers of review by NASA, ESA, and CSA. All of these safeguards are meant to protect science, but they also slow the story to a crawl. Meanwhile, what we do know remains both tantalizing and incomplete. A vast coma stretching hundreds of thousands of kilometers, whispers of a carbon dioxide-rich composition, unlike the water-dominated comets we know best. A persistent green tint that refuses to fade, a shifting plume whose behavior defies easy explanation, and brightness scatter that may point to sudden real changes in activity. Each clue is compelling, but none yet provides the full picture. As Mars orbiters prepare to capture fleeting data during the close pass, and as perihelion draws near at the end of October, the world waits. Will the comet hold together? Will its chemistry shift? Will the green glow dim, or will it blaze even brighter as it swings around the sun? By December, when Hubble and Webb regain access, we will finally have the chance to see in detail what the comet has become. Until then, all we can do is watch with cautious eyes, compare notes, and resist the pull of wild speculation. The story of 3I Atlas isn't finished. It is only turning to its next page. Whatever happens, this interstellar traveler reminds us how much of the cosmos remains hidden, how much patience science demands, and how much wonder still waits beyond our reach. I'm Mike, and this is Lamora.